Hello wonderful person, this is Anton, and today we're going to be discussing some really intriguing discoveries when it comes to the idea behind galactic evolution. And that's because normally when astronomers discuss galactic evolution or galactic growth, we often think of galaxies as these massive, stable structures, mostly governed by slow, predictable dance of gravity over billions of years. Something that scientists can even simulate using various supercomputers that essentially produce massive galactic structures that evolve over time. But turns out, based on some of the recent research, quite a few assumptions in these simulations might have been just a little bit incorrect. And specifically because galactic growth and the evolution of galaxies like the Milky Way may be a little bit more chaotic than we imagined. And specifically, it turns out that even changing a tiny little parameter, or specifically a position of a single star, could potentially reshape the entire galaxy. And to understand why this is so unexpected and so unusual, we obviously first have to discuss what we already know about galactic growth and how galaxies like the Milky Way normally develop. And here astronomers often use what's known as chemical fossils to try to piece together the past of a typical galaxy. This is actually sometimes referred to as galactic archaeology. And that's because stars are like tiny chemical factories which accept simple hydrogen and helium and fuse them into something more complex like oxygen and iron. And so when the stars die and when they transform into something else like a black hole or a neutron star, they seed the galaxy with a lot of new materials through powerful supernova. And that, of course, creates the new generation of stars. And by looking at this chemical complexity, we can normally work out where some of the stars potentially started and where some of the new generation of stars seems to reside as well. For example, for the Milky Way galaxy, we know that a lot of ancient stars seem to reside in the thicker disk or on the outskirts of the galaxy, and the much younger members seem to be inside the thin disk and also closer to the center. But for an extremely long time, astronomers also assumed that since the galaxy contains hundreds of billions, if not trillions of stars, any small local disturbance would simply be averaged out, or basically just be some kind of a statistical anomaly, but would not really have much effect. And so for the most part, we treated galaxies as these smooth systems, which is essentially what all of these simulations are based on. But this new study we're going to be discussing today, the study by Tetsuro Asano and Simon Zwart, used a massive computer simulation to show that the smoothness might be an illusion, and is simply caused by our simplification of actual math. And that's because in these simulations, researchers decided to do something very specific. They created two nearly identical versions of a Milky Way-like galaxy, or essentially a spiral bar galaxy, with the only difference being an almost infinitesimal perturbation, and specifically, they moved a single star by a tiny amount somewhere inside the galaxy. And in other simulations, this would be basically equivalent to a kind of a rounding error. So essentially, most computers would ignore this. And well then, they let these galaxies evolve for several billion years, with the results clearly showing us something that you might remember from a concept that trended a few years back, the butterfly effect. This was a clear manifestation of the butterfly effect, but on astronomical proportions. Here's actually a demonstration using double pendulums, and it basically shows us that even a tiny perturbation or a small change in the system's initial stage can lead to massive differences later on and produce extremely different final results. And it's usually referred to as the butterfly effect because, for example, a butterfly flapping its wings somewhere in Brazil through the concepts of chaos theory could possibly cause a tornado in Texas. And so something somewhat similar seems to apply here as well. Here in the simulated galaxy, that one tiny shift caused the spiral arms to develop in a completely different pattern, with the central bar of stars rotating at different angles. You can visually see the differences right here. So even though it's still kind of similar, in terms of the actual shape and appearance, these two galaxies look very, very different. And so it's not that the stars are in different positions, the entire galactic shapes develop differently too. And this is of course important because it suggests that the Milky Way simply becomes unpredictable after just a few million years, even if a tiny star is shifted by a little bit. And though a million years might sound like a long time, for a galaxy that's most likely over 13 billion years old, that's essentially just a blink of an eye. And this means that if we could go back in time and move just a single star, the night sky we would be seeing today would be entirely different. So definitely a pretty exciting discovery just based on this one simulation. But here there's also a somewhat fascinating discovery when it comes to the limit of the chaos theory. And that's because here the study discovered that while the fine details like the spiral arms have changed, the big picture events were still actually the same. So for example, a central bar of stars always formed at roughly the same time in every simulation. In this case, regardless of these tiny changes, which to some extent resolves this long-standing paradox, essentially confirming that technically galaxies can be both chaotic in certain details inside the galaxy, but also kind of smooth and even kind of predictable in their overall evolution over time. Which is of course great news for a lot of these simulations because overall the results are obviously not incorrect. Here only specific details and specific location of stars might be affected. But there are still some unanswered questions. For example, why did nobody ever notice this particular chaos before? Or specifically, why didn't previous older studies ever see this happening in real time? And well, here it seems to come down to something referred to as gravitational softening. Since calculating gravity between billions of individual stars is incredibly difficult for computers, scientists often treat stars as softened clouds and not just point masses. In other words, in a typical simulation like this, individual particles don't really experience gravity between each other. There is a lot of averaging going on, and there are a lot of mathematical shortcuts, which effectively kind of muffles a lot of this chaos. With Asano and Zwart showing that as you make these simulations a lot more realistic and less softened, this chaos becomes almost impossible to ignore. In other words, the more realistic you make the simulation, the more chaos it creates. And so here this creates a kind of a paradox of infinite granularity, which suggests that the real universe is likely orders of magnitude more chaotic and thus more unpredictable compared to the best possible model we can currently create, which potentially explains why none of the models seem to actually predict the universe very accurately. With this, of course, having a lot of implications on galactic archaeology, since quite a lot of studies have actually used these ideas and tried to combine them with observations from the Gaia telescope, mostly to reconstruct some of the previous years of the Milky Way galaxy. Here we now know we have to be super careful. But in the past, scientists have discovered that, based on some of the initial simulations, Milky Way definitely had at least a few specific collisions. For example, the Gaia-Enceladus collision 11 billion years ago, which triggered a massive burst of star formation inside the galaxy. And while here we can only see these major events, according to this new study, we still must be very careful when trying to trace the exact orbits, or if we try to discover exact locations of individual stars. And so in short, this confirms this idea of the butterfly effect even on the cosmic scales. Or basically we live in a universe where even the smallest objects, like very small stars, can influence the formation of the largest structures around them, confirming that stars, and possibly even smaller objects, are not just passive passengers, they are the engines that define the galactic shapes, and their individual flapping wings seem to determine the long-term fate of the entire cosmic system. Which of course makes the night skies we see today just a little bit more meaningful, because in this case, even the sun very likely had some effect on the formation that we see. And so essentially the order in the Milky Way is a lot more precious than we believed. But when it comes to the exact mathematical discoveries, when it comes to our galaxy, there was actually something else that was somewhat interesting, and it's actually referred to as the Lyapunov time. This is a mathematical term, named after a Russian mathematician that came up with it, that represents a time scale over which a system's memory of initial conditions is lost completely. Normally due to some kind of an exponential divergence, or basically a lot of chaos. And well, over the years, mathematicians were able to calculate this for a lot of different systems quite precisely. For example, when it comes to various chemical reactions, and specifically chemical oscillations, usually all of this becomes too chaotic after just 5 minutes. Whereas for larger objects, such as moons and planets, the Lyapunov time is normally in millions of years. Here's actually a really good example, Pluto's orbit. It's approximately 20 million years, after which everything becomes too unpredictable. But for the Milky Way-sized galaxy, turns out that this time is even shorter, only 0.1 million years or 100,000 years. So basically even shorter compared to what we usually find in the solar system itself. And so after just 100,000 years, the entire galactic system becomes too unpredictable and will usually create very different final results depending on the initial conditions. And so in cosmic timescales of billions of years, this is actually pretty tiny. It actually suggests that galaxies are incredibly sensitive, and even the movement of a couple of stars can change the entire structure in just a few million years. And though this simulation only used 40 million particles, they also confirmed that by increasing the number of particles, the overall complexity and the overall chaos increases as well. And so by simulating 400 billion particles, like in a typical galaxy, here the overall system would become even more chaotic. But I guess the biggest surprise was really the fact that even huge structures like galactic bars seem to be very sensitive to these minuscule conditions. And so the evolution of galactic bars and galactic arms changes dramatically depending on what you start with. And so definitely super exciting discoveries for astronomy and for understanding the complexity of cosmos. But until future studies or until someone else attempts something even more complex, that's pretty much all we know. Thank you for watching, subscribe, come back tomorrow to learn something else. Support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.